We've talked about probability distributions and means and variances of different probability distributions, or I'm sorry, general probability distributions. But what we're going to be doing in the next several sections is developing a collection of certain types of probability distributions that pop up in practice quite a bit so that we can recognize what the distribution is and how to deal with the questions that will be asked about those particular distributions. So the first one we're going to talk about in depth here is what's referred to as the binomial distribution. And to get to the binomial distribution, we need to talk about what Bernoulli trials are. So the first part here, the first definition we have is what we refer to as a Bernoulli experiment. Again, a random experiment, there's only going to be two possible outcomes. Usually we refer to those outcomes as success and failure. So for example, one way to think of a Bernoulli experiment would be to flip a coin, right? Two possible outcomes, heads, tails. Now, again, you could think of either one of those as being success, and then the other one would be failure. But some other options is maybe you would roll a die, and you want to see a 3. So maybe you do 3 and not 3. That's two possible outcomes, right? I either get a 3 or I don't. So in that case, maybe you call getting a 3 a success, and then the probability of success in that case would be 1/6. And usually, if we're doing this generally, we refer to the probability of success as P, which automatically tells us what the probability of failure would be. It would be 1 minus P. Because again, we only have those two possible outcomes that can come out. So when we have a Bernoulli experiment and we use what we refer to as a Bernoulli random variable, we need to begin to convert those to numbers. So we'll say that success has a value of 1, failure has a value of 0. So we can write the PMF pretty easily if we just write it down, right? Probability of x equals 0, that's probability of failure, that's 1 minus P. Probability that x is equal to 1, that's P. That's what we use for probability of success. Okay. A little bit more succinct and maybe call it clever way to write this is f of x is p to the x and 1 minus p to the 1 minus x, where x is either 0 or 1. Notice if you put in x equal to 0, that should give me failure, right? Well, if I put p to the 0, I get 1. And I get 1 minus p to the first, I get 1 minus p like I have up here. Likewise, if x is equal to 1, I get p to the first, 1 minus p to the 0, so I just end up with p, which is our probability of success. Let's compute the mean and the variance of this particular distribution. Well, there's only two possibilities for x, right? It's 0 and 1. We know the associated probabilities, so we get P. We can do the same thing for expected value of x squared. All we do is square the outcomes, but 0 squared is 0 and 1 squared is 1, so we still get P for that. And now if we want the variance then, I would get P for expected value of x, P for expected value of x squared, P for expected value of x. We square that part, so we get P minus P squared, and we can factor out a P to get P times 1 minus P. So this gives us mean and variance for a Bernoulli experiment. All right, let's suppose instead of just doing this one time, we do this experiment a whole bunch of times. So maybe you flip a coin 15 times. Okay, that would be doing a Bernoulli experiment over and over and over again. We want the experiments to be independent, like the coin flipping example, right? If I flip a coin, it doesn't affect the next flip, and it doesn't affect the next flip after that, and so on down the line. The experiments are independent, and the probability of success stays the same no matter what. And if you flip a coin, you should always have a probability of heads as being a half, probability of tails being a half. We refer to this as what's called a sequence of Bernoulli trials. Usually, if we're dealing with a sequence of Bernoulli trials, we're trying to count how many successes happened in the total number of trials. So if you flip a coin 15 times, maybe you want to count how many times heads came up. Okay? If you roll a die 78 times, maybe you want to know how many times a 4 came up. Okay, you're counting the number of successes. And it should be, say, successes instead of number of success. It's a typo. It should say successes. All right, so to that end, let's say we have a random variable that counts the number of successes in n Bernoulli trials. All right, so remember, capital X takes on some value little x. If we have little x successes, then we also have n minus x failures. They're all independent, so we can calculate probabilities by multiplication, right? So if we have n successes, or excuse me, if we have x successes and the probability of any success is p, the probability of having n successes will be p to the x. Sorry, the probability of having x successes is p to the x. But remember, we also have n minus x failures. Probability of failure is 1 minus p. We have n minus x of those, so I have 1 minus p to the n minus x to get n minus x failures. And since we need x successes and n minus x failures, the independence says multiply those two things together. So if any, then this is for any sequence of trials that has x successes and n minus x failures, right? This will give me the probability. However, there are lots of different sequences that have x successes and n minus x failures. For example, say you flip a coin 5 times and you count number of heads. Well, if you look for when there's 2 successes, you might get heads, heads, tails, tails, tails. But you could also get tails, 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 heads, heads, and several other possibilities, right? It's not just one sequence that gives you x successes and n minus x failures. There are several. So we need to count how many of those possibilities there are. So let's think of the trials numbered 1 through n. What we're going to do is we're going to choose which of the trials are successes, because once we pick where the successes are, the failures are automatically determined for us, because there's only 2 possible outcomes again. So in this case, if we're going to choose which trials are the successes, we have n objects to choose from, the numbers 1 through n, and we're going to choose x of them, where the successes should be. We're going to do that without replacement and without worrying about order, because if I say successes are in trials 1 and 4, that's the same thing as being in 4 and 1. We don't really care the order. So that means we have a combination problem here, and so there are n choose x possible sequences. All right, so now the probability of exactly x successes in trials, remember this was a given sequence had that many successes, and this is how many of them there are. So this gives us the probability of having x successes in n trials. It's this n choose x, p to the x, 1 minus p to the n minus x. And the support here is 0 through n because, again, we're counting number of successes. Worst case scenario, you had no successes. Best case scenario, you had all successes. We refer to this PMF as the PMF for a distribution called a binomial distribution. And binomial distribution comes up a lot in probability, so this is one that you're going to be intimately familiar with by the end of the semester. So let's just put it in action, and then we're going to save some of the more interesting properties of the binomial distribution for class and do more examples. But let's just do a single example here to put it in action. Student didn't study for a test. Let's say the test has 10 multiple choice questions, so the student's just going to guess. I didn't study. I don't know how to do this. I'm just going to randomly guess answers. 4 answer choices for every question. Only 1 possibility for each question. There's only 1 correct answer. What's the probability that the student answers exactly 3 questions correctly? All right, so correct here, a correct guess will be your probability of success. So our P is 0.25, 1 out of 4. There's n questions, there's 10 questions, so our n is 10. And we want to know 3 questions answered correctly. So our number of successes, our x value here is 3. So our PMF here gives us the probability that x is equal to 3. So we plug in 3, and if we simplify that, we should get 0.2503 if I did that in my calculator correctly. So, like I said, we'll do more of these examples, but this is the idea. I'll show you some different calculator functions that will allow us to do these a little bit more quickly. Show you a little bit of Excel too if you're doing these outside of class. You can certainly use Excel or your calculator to get these values. I just want to show you a couple of things that will help you evaluate these more quickly. So, all right, we'll talk about this more in class.